Alright guys, so this afternoon we're going to take a look at linear momentum and collisions. Okay, that's going to be like the start of a new unit kind of thing, right? It's kind of related to energy, but um, in the sense that you'll see as we come up with what momentum actually looks like, it looks very similar to kinetic energy. Okay, so obviously I think like momentum, like that's just kind of an object's willingness to continue moving in a particular direction, right? Um, and so we're going to see that exact statement in the way that the equation comes out. Okay, so the linear momentum of a particle of mass m moving with a velocity v, okay, is defined. And what you'll notice is what we did here is we said the velocity was a vector, right? Is defined to be the product of the mass and the velocity. Okay, so that's pretty much exactly what I said. It's an object of mass m, and its willingness to move in a particular direction. The direction and movement being controlled by the velocity vector, right? Remember, we're going to have a magnitude and a direction with this, right? So we're going to have the product. Okay. And so what that looks like is we typically denote we denote momentum with the letter P, lowercase, sorry, right, is equal to the mass of the object multiplied by the velocity that it has. Okay, and there's units, right? We can see that come out. You know, there's the dimensions, right? So there's the mass and there's the dimensions for speed, okay, or velocity. Okay, so Newton's second law, okay, states that an object acted upon by external forces accelerates in the direction of that net force. Okay, and we already saw that back in Unit 2, right? And so if we looked at the sum of the forces, if the sum of those forces does not equal 0, then the object has to accelerate, right? So if the net force on the system is not 0, we're going to see a net acceleration in the direction of that net force. That's what that statement's saying, right? And so we can run with this, right? We know, if I were to look at way back to kinematics, we know that the acceleration, we could write the acceleration as being okay, that looks like one of our kinematic equations just rearranged. Okay. If I'm not mistaken, that will be V2 will equal V1 plus AT. Okay, that's where that came from. Okay, that's just a kinematic equation we isolated for A. So what we're going to do is we're going to replace A in the equation with this. Okay, and we did this somewhere else as well, where we would substitute acceleration in for the acceleration in F equals ma, and we were able to derive an equation. That was the actual, when we did kinetic energy, that's where we saw that. Okay, so very similar, right? So all we're going to do here, I'm going to try and get rid of the fraction on the right hand side, right? And to do that, so I'm just going to rewrite this line here. I'm going to get the sum of the forces, right, is equal to m, and then I'm going to make the substitution for the a that we found, v2 minus v1 over t. And we can call it the change in time, I suppose, right? And then I'm going to multiply, to get rid of the fraction, I'm going to multiply both sides by delta t, right? And I'm going to cancel on this side. And we're going to see that the equation here, sum of the forces, is multiplied by delta t is equal to m v2 minus v1. Okay, and if I were to go one step further, I'm going to go I'm just going to distribute the m into the brackets. Okay, and we arrive at something that looks a lot like this, right? Well, what does this mean, right? That's kind of where we're at. Well, we could say, well, we already knew that up here, momentum was equal to the mass times the velocity, right? And so we could try and make that substitution there, right? So we could say, okay, well, the sum of the forces multiplied by the change in time, we don't really know what this is yet. We're going to learn about that in a minute, right? That's, well, the momentum final, so P2 minus P1, okay? And we saw over and over and over again, anytime you guys do this, like, right? I'll go right back to grade 9. This is what we call a change in, right? Which we can denote as delta, right? Delta is the change in. So the sum of the forces is the change in momentum. Okay? And I can do one more thing here, right? I could say, okay, well, the sum of the forces could be equal to the change in momentum over the change in time. Okay? Remember, I suppose the whole way down, maybe we should have been doing like a vector, right? Because the momentum is going to have direction on it from the velocity, right? So what is this then? What is this thing? Well, F delta t, this describes how an object's, or the force acting on an object, is changing relative to time. Okay, so basically what we're saying is if we saw that if I were to produce an acceleration time graph, in the very first unit, in kinematics, we saw that the acceleration would always be kind of constant, right? Our graphs would look something like this, right? If this was a accel versus time. Okay, that acceleration was created by a constant force, right? Whereas this time we're looking at how that force is changing relative to time. Okay, and so we create this new phenomenon, right? Because we haven't seen this before, right? Everything we've dealt with up until this point, forces have kind of remained constant in order to produce accelerations, right? And so we have to be able to define what this is, right? This turns out to be what we call impulse. Okay? And we denote it as J with a vector, right? Because, again, we're getting the vector notation from the velocities, right? The velocities are going to have vectors. Okay? Now, to use the word J, or the letter J, you might ask yourself, why are we picking J with impulse, right? Well, J can also stand for jerk, right? And this is what you would experience in a car if the car accelerates and then like it's accelerating and its acceleration changes, right? So for instance, like in a manual car, you might accelerate, and then for that split moment in time when you change the gears, right, the car slows down, and then the car goes back into gear and you feel that jerk. It's a change in acceleration, right? That's the jerk or impulse that we're measuring, right? And we can actually measure it by looking at what the final velocity is and what the initial velocity is. Okay. Okay, and so the units on this Or we could write one more thing. Jerk or impulse is equal to the change in the momentum. Okay? And its units are going to be the Newton seconds. Okay? And just one other side note, I suppose, too, is that it, like, from coming from like a if we're looking from a math lens, right? Jerk or impulse is going to be the third derivative of the position time graph, right? Or the first derivative of the acceleration time graph, which is what we were talking about here, right? So you're looking at the rates of change of the acceleration time graph, right? Which is exactly as I've described with the motion of a manual car, right? Where the acceleration changes in that split moment and you feel that like jerk, right? Or impulse. Okay, so instead of having constant, horizontal lines imply constant, whether it was velocity or acceleration, constant acceleration. What jerk and impulse are dealing with is where your acceleration time graph is now going to have a slope, right? And so we can find the derivative of whatever curve we have on our acceleration time graph. And that's going to denote the impulse at any particular time. Okay. So if we come down here, I'm just going to run through a couple scenarios here, right? Like, during a collision, an object experiences an impulse that changes its momentum, right? So anytime you see a change in the momentum, that's what we described up here, right? Change in momentum, delta P, right? That's this. Okay, we're going to see that the impulse is equal to the momentum change. Okay, and you can see there that for catching a baseball, right, the second velocity, right, once you've caught the ball is 0, right? But we're going to still subtract off the initial velocity, right, which ends up producing a negative impulse. Right? That's what this is saying here. Okay, v2 is going to be 0, and so you end up getting a negative impulse. Okay, and so for calculating the sum of the forces, they're like F net, right, is equal to the change in momentum over time. In an example where we're still catching our baseball, if we were to increase the time, right, so what we're talking about is we increase the denominator of a fraction, right, we better expect that the number gets smaller, right? So something 1/4, right, or 1/5. 1/5 would be smaller than 1/4, right, because we've increased this number, right? So if we come down here and we're looking at, okay, well, we have the change in momentum over the change in time. If I increase the time in which something is happening, right? So for instance, catching a baseball, if you move your hand with the ball, right, you're going to increase the amount as you're catching it. Sorry. So if you move your hand as you're catching it in the same direction as the ball, if the ball's motion, you're going to increase the amount of time that the ball is experiencing this deceleration, we'll say, okay, or the change in momentum, right? You're increasing the time and the fraction increases, the magnitude of the fraction decreases, right? And so we see that the amount of force exerted on your hand goes down for this reasoning here, right? As we increase the time of impact, the force exerted would have to go down, okay? Or impulse or jerk, right? So the amount of impulse that you would feel in your hand, right? The change in acceleration would occur over a larger amount of time. Okay. And so we can find what impulse looks like by, if we were to graph the force by the time, we'd be able to actually look at the area underneath that curve, and that would tell us our jerk or impulse. Okay. So that's like an introduction to this, right? Really, we're just going to apply the equations now, right? Stuff that we came up with. So it's not much different than anything that we've seen before, from the standpoint that you're going to be given some knowns and some unknowns, and we're just going to try and find the things that we're asked to find in the question, right? So, for instance, a personal watercraft and its rider have a combined mass of 405 kilograms and a momentum of 5,020 kilogram meter seconds. Okay, west. Okay, we want to determine the velocity of the craft. Okay, so it's not too bad. Well, why don't we start with, we know that it gave us a mass. So the mass is going to equal 405 kilograms. And then we know that it has a momentum of, so a p-value of 5,020 kilogram meter seconds. Okay. And we know that, well, we want to know what the velocity is. And keep in mind, it did tell us a direction here in the question. Okay, then we're going to come back to that. So we know that momentum, or p, we're just going to our equation now, p as a vector is equal to the mass multiplied by the velocity of the vector, right? We could say, we do know that the momentum of this is going in the west direction. Okay, you guys can add that to your knowns, right? But so we're going to say 5,020 is equal to the mass, 405, multiplied by the velocity vector, right? Right, you guys can just solve for the velocity and know that this thing's going in the west direction. So if you were to divide both sides by 405, you'd find the magnitude of the velocity would be 12.4 meters per second. Okay, and I suppose, now that we're getting into this, if you guys were to assign a coordinate system, as we normally should, and I did not, right? This would be north, east, south, and west. The way you could control the sign, if you didn't want to write west everywhere, remember, we can just make the momentum, instead of being west, we can make the momentum negative, right? Because west is in the negative direction. So our answer could be negative 12.4 meters per second, or you could say 12.4 meters per second west. Okay, that's not too bad. That's just an introductory question, right? So we can see that if an object's motion or momentum is going in any particular direction, I'm just trying to reiterate what I said this morning, the very first thing, right? Is if an object is moving in a particular direction, right, we can see that in its velocity vector, right? But the momentum has to follow that velocity vector, right? We can't just have momentum in the opposite direction. That doesn't make any sense. So it makes sense from the standpoint that because velocity is a vector, momentum must be a vector, right? Because mass is kind of a scalar, or it is a scalar, not kind of, it is a scalar, right? And so when you combine the two, that object has to have momentum in the direction that it's moving. Okay, that's what we can see here in the answer. Okay, so a 57-gram tennis ball is thrown upward and then struck as it comes to rest at the top of its motion. Right? The racket exerts an average force of 420 newtons on the tennis ball. Okay, we want to determine the speed of the tennis ball after the collision if the average force is applied to the tennis ball for 0.0045 seconds. Okay, so let's just do part A. Okay, and we're going to see something interesting happen here that I said above around this stuff, right? The fractions. Okay, we're going to see what happens here. Prove it numerically. Okay, so we're going to look at the average force right? So we want to look at, okay, well, let's look at what forces are acting, right? In this particular question, right? And I suppose I'll write this out first. So we want to look at the sum of the forces, and that's going to if we multiply that by delta t, right? That's going to equal the mass times the velocity. Okay. And so we can look at, I'll move this down here for a sec, because I always like starting these questions with things I know and don't know. Remember, our units are in kilograms. Okay, so this is no use to us in grams, right? Right? We got to switch that to kilograms. So 57 grams, right? 0.057 kilograms. The seconds is fine, so we know the time, so the change in time, right? Just the change in time, we went from 0 to this current time. So delta t isn't that interesting from that standpoint because one of the times is 0, right? And we know that the average force applied to over this time was 420 newtons, right? We're looking at such small times that the average force, we can use the average force because really it's such a small amount of time, right? And so with small amounts of time like this, the variation in that average force is probably not very big, all right? Which is why we can get away with using the terminology or finding the average force during that small amount of time. Okay, so we want to look at this equation now. It looks like we have most of what we need, right? We're looking for the velocity when it leaves, right? Okay. Now this question wasn't very particular on directions or anything like that, right? So I suppose we're just looking for the magnitude of the velocity, right? As it leaves, or did it specify speed? No, it did say speed. That's why we're not using any vectors, okay? Just looking for the speed, the magnitude of the velocity, okay? So we're just gonna throw in the numbers that we have. We have 420 multiplied by 0.0, that looks like a minus. Maybe I'll put them in brackets. Let's do a little bit of isolation too, sorry. So, or not b, I want to divide by m. Right, those are going to cancel. And so the velocity is going to equal 420 multiplied by the time divide by the mass. Right? And so, sorry, I'll stop using the word velocity. This is velocity. We're looking for speed here. The speed of the tennis ball when it leaves the racket will be 33.2 meters per second. Okay. And let's take a look at part B now, right? So we're going to repeat this exact same question, right? Except we want to look for how is this going to change if we increase the time that the ball is in contact with the racket. So let's just see what happens, right? We could take a guess based on what the equation is going to look like, right? But we're going to have the same derivation. So we know that V is going to equal the average force or some of the forces over some time and divide that by the mass. Okay, we're going to say, okay, well, we're going to say, let's just plug in the stuff. It's the same force being applied because it's the same racket, so it's 420, right? And then we're going to multiply that by the time again. But this time, oh, sorry, change the time. We change the time to this one. Okay, so that's what we're going to put in there, 0.0053. And it's the same tennis ball, so the mass is the same, 0.057. Okay, what happens? Well, it turns out the number is 39.1 meters per second. Okay, so if we increase the time that this particular object is able to be in contact with the racket, then the velocity goes higher, or speed, sorry, speed goes higher. Okay, velocity, if it would leave in the positive direction, let's say. Okay, well, what's that mean? Well, you see this a lot in golf, right? There are rules, and I'm sure the same thing in tennis. There are rules limiting golf manufacturers of, like, let's say drivers or any kind of golf club actually, for the amount of time that a golf ball can spend on the face during impact. Okay, and that's for the reason that obviously if the ball leaves with a higher velocity, it's going to go further, right? And so where's the limit, right? And so the USGA draws a limit, right, to say, well, the ball can't spend this amount of time on the face, and that's it, right? Any more, it becomes an illegal club for tournament play per se, right? It's not to say that people don't still make them, but anyway, you can see there, it's like a little bit of proportional reasoning there, right? We're looking at a particular question and we're looking at the variables involved, and we're like, well, what happens if we increase this? Well, then this should change, right? And vice versa. Okay, so we increase the time, we increase the velocity. If we increase the mass, we would decrease the velocity, right? Because now the denominator would get smaller, or sorry, bigger, so the overall fraction would get smaller. Okay, and so the velocity would go down. So a statement like, and you might see some of this in university too, is like they'll put a thing, let's say, okay, well, what happens if I increase mass, then I decrease velocity, and they might have a whole bunch of these, right, as statements, and you have to select the correct one based on the context of the question that you're dealing with. Okay, so that could be a type of question you see in university. Okay, I got a couple more two more examples here. Okay, we'll try to go quick here. Wrap this up. Okay, I don't know how long we're at here. Not too bad. Okay, so a baseball of mass 0.152 kilograms, traveling horizontally at 37.5 meters per second. Okay, collides with a baseball bat. The collision lasts for 0.00115 seconds, and after the collision, the baseball travels horizontally at 49.5 meters per second west. Okay, so we're dealing with velocities here. Okay, so make sure your answer has a vector, like vector notation, right? So determine the change of momentum of the baseball. Okay, well, change in momentum sounds like something I've heard of before and what you've heard of before, right? That sounds like jerk is the change in momentum, right? Or impulse. What is the change in momentum? Well, let's just do that part, right? We're going to say, okay, well, we know that delta P has to be P2 minus P1, which will be mv2 minus mv1. Okay, so let's just do these two calculations separately. We'll find the momentum finally and what it was initially, right? And we can calculate the impulse after. Okay, we'll just put it back into there. So let's do part A here, or I say part I will say is find P1. Right? And we're going to say, okay, well, P1 is going to equal the mass of the baseball, 0.152, times the velocity that it was traveling at, 37.5 originally. Yep. Right? And you should get a number of 5.7. Okay. And because it's a vector, we're going to have east, right? Like initially, remember after the fact, the baseball travels horizontally at that west, right? So initially, we must have thrown the ball east, right? So again, it might be a good idea to set up a coordinate system, right, where we know positive, positive, negative, negative, okay? So this answer is fine. We could leave it as positive, nothing too crazy there. But then we could do part 2, where we find the momentum after the fact. Right? And we're going to see, okay, well, it's the same baseball, but this time it leaves at 49.5 meters per second west. Okay. And we can find that the momentum finally would be 7.5 in the west direction, okay, or negative. You can make it either or, right? Because you didn't want to include the directions. Just notice I've specified the directions on each of those, okay? And so what do? Okay, well, we take P2 minus P1. We want to find what the actual impulse or jerk or change in momentum is. All three of those things are the same thing, right? Impulse, jerk, change of momentum. So how do we do that? Well, we take the two numbers that we found and we just put them in up here. We can find that the jerk or impulse is going to be P2. Well, P2 we found to be negative 7.5, and P1 we found to be minus 5.7, right? And so we get negative 13.2. Right? Which direction? Well, it came out negative, right? So we could say, okay, well, it's 13.2. In the west direction. Okay, that'll be the answer for part A. Okay, and then part B here is asking us, and maybe you want to leave, maybe for the purposes of actually working with the problem, it's important to have the direction. So you might choose to work with this actual numeric, right? So this answers the question at hand. It's like, well, which direction is the momentum in? Well, we know what west is. I mean, the negative tells us that too, but in case, I think the west is obviously very clear as to where the ball is headed or the momentum of the ball, right? But for the context of the question, it's important that this negative is there, okay? And we've seen instances of where not having a negative messes things up, right? So we're like, okay, well, what's the average force? So let's write down our equation. Well, the average force is going to be the change in momentum over how long it took for that change in momentum to take or to occur, right? And so we're going to have delta P is going to be negative 13.2 over how long did this impact take place? 0.00115, right? And so the average force exerted by the bat on the ball will be 11,478 newtons in the west direction. Okay, you can also leave it at the negative as well if you'd like, instead of having the west. As long as this is here. As long as you've told me what the coordinate system is and everything makes sense, checks out what negatives mean, what positives mean, then we're okay. The important part is that you're remembering the importance of what vectors are and that they denote both magnitude and direction. They tell a story, right? If you just put down a number, that's half the story. Okay, one last question. A ball of mass 100 grams is dropped from a height of 2 meters above the ground. Okay, it rebounds vertically to a height of 1.5 meters after colliding with the floor. Okay, we want to find the momentum of the ball immediately before and after it collides with the floor. Okay, that's part A. And then part B is basically the same. We want to determine the average force exerted by the floor on the ball. Okay, and we're going to assume that the time of the collision is 0.01 seconds. Okay, so a little bit trickier here, this question. We're like, okay, well, what are we given? I would say let's start with what we're given. Okay, well, we know the mass of the ball. The mass of the ball is going to be 0.1 kilograms, right? 100 grams. And then we know, okay, well, it got dropped from 2 meters above the ground. Okay, so we know H equals 2 meters. Okay. And then it rebounds vertically to a height of 1.5 meters. Okay, so we call this, H1, and H2 will be 1.5 meters. Okay, so we're in a bit of a jam here, right? We're like, okay, well, we can't really use this momentum thing, right? Quite yet. It hasn't really told us much, right? Based on everything that we've done this morning, or this afternoon, sorry. Okay, so what are we going to have to do? Well, let's set up. It doesn't really tell me anything about the velocity, right? So that's kind of my main concern right now, is I don't really have anything about the velocity. But we learned this morning about a nice little theorem, right? And it was conservation of energy, right? Well, we had a ball at a height of 2 meters, right? And then it finished at a height of 1.5 meters, right? So we could say, okay, well, we know that the energy before has to equal the energy after, right? And we can use that argument to help us. Okay, so we know that. Let's look at before. So before, we knew that the height was going to be 2 meters, right? And then we let it go. So initially, the energy of the ball would have been all potential, right? mgh, because we're holding it. There's no motion. And then after, right? And we're looking at the split instance before it hits the ground, right? So it's virtually at 0, right? So if I'm thinking like afterwards, I'll write all this out because I think it's worth navigating. Okay, so initially, V1, we were holding it, right? And so the velocity was 0, right, initially. But we had a height, okay? Then after the height, we were looking at the very split moment before it hits, or as it's hitting the ground, right? Just before. So we're going to assume that H is negligible in that split moment, right? So we're not interested in this is 0, right? And so what do we get? Well, mgh, we're assuming that under the circumstances here, all of this potential energy has been converted into kinetic. Okay? And we know that the mass of the ball didn't just change, so we know that the masses can cancel. And so all you need to solve for is the velocity as it's about to hit the ground, and we can find what the momentum was before it hit the ground, right? And so we say, okay, well, that's fine. So let's just find V2. Well, V2 is going to equal the square root of 2GH. So V2 is going to equal 2 times 9.8 times the height that it was dropped at, 2 meters, and square root that. Right? And so V2 should equal Actually, you know what? We're going to do something clever here. Let's leave it at that. I'm going to try and teach you guys something. We could get a number. And if you're comfortable getting a number and continue work with that question, do that, okay? But for the purposes of what I'm trying to show you here, we'll leave it at there, okay? We know what V2 is now, no problem, right? But I want to leave it like this. The other thing is I kind of distinctly remember sometimes, you know, having to solve questions algebraically for university questions, right? Where you're like, they don't necessarily give you numbers, but all your options in the multiple choice are all variables, right? And so working with variables in algebra is okay sometimes, right? When you're not provided enough information. You can still kind of like contextualize what the answer is going to look like from the standpoint of algebra, okay? So we're going to make this exact same argument after the fact. So I'm just going to shrink it down because I need a little bit of room, okay? I'll move it up too. So there's the energy statement for before, and then we're going to do the exact same argument after, right? And after, we should see that after the ball makes contact with the ground and leaves, right? We know that V2 will equal the exact same thing. Okay, what I'm going to do here, guys, is, and I'm just realizing this now, I'm going to change these V2s to V1s in the context of the entire question. I didn't intend on doing this to show you where it came from, so I would have originally put the V1 there, but so, and I'm doing this because when I look at the change of momentum, I want that to be mv2 minus mv1, okay? And so this would be the velocity after, and this would be the velocity initial. And so I want this to go in there, and I want this one to go in here. So this would be H2. This would be H1. Okay. Anyway, that's why I'm doing this. Sorry. Okay. So we can now find what the change in momentum would look like, right? And I think we can actually plug in the numbers now, right? And be fine. And I suppose you could have done that here. It's not an overly complicated question from the standpoint of the algebra, but we could say, you know, if you didn't want to do all this math all and like you just want to do it in one line at the very end, you could do, okay, well, the mass hasn't changed. V2 we know is going to be this 2 times G times H2 minus, oh, and that has to be square rooted, right? And we have to subtract off M and what the V1 was, 2GH1 square rooted, right? Now you could plug in your numbers and have no problems. We're going to find the change in momentum here, right? Because that's what it was asking for. Find the momentum immediately before and after. Oh, okay. We can find the change in if we would like to, right? But both of these would allow us to find what the momentum was before and what it was after, okay? And we know eventually anyway, we're going to need to know what the change in momentum is and to find what the average force was exerted, right? And so I'm just setting it up like this. So I can find what the momentum was before the collision and what it was after, right? That should have been flipped. So this is all before and this is after stuff, right? So let's just type that stuff in. We'll see what the two numbers come out to be, and we'll actually find the change in momentum at the same time, which is, we're killing two birds with one stone here. Okay, so change in momentum, we're going to find that the mass, 0.1, it should be multiplied against the square root of 2g 2 times 9.8 times 2. And we're going to subtract off 0.1 times 2 times 9.8 times 1.5. And that has to be square rooted, okay? And what you'll find is we should see that the momentum comes out to be after, so the V2 piece should be 0.542 minus right? And the momentum after is up, right? Because it's made contact with the floor and the momentum switched to go back up again. So it makes sense that this is positive, right? And afterwards, the momentum should come out to be negative because it was acting in the negative direction, right? And that's why it's taking care of that. So we're going to see that this should be coming out as negative, right? So we should see negative 0.626, right? We know when I released the ball in the first place, the momentum's acting downward. That's what this sign is for, right? The negative there. Okay, now we can just do the math on that, which I haven't done. So we got to do that. We're almost done this question, right? So we need to go, I don't know what this is. Maybe a bracket, meant to be bracket. 0.542. And we're going to add, right, because the two negatives come out to be positive, 0.626. That's going to equal 1.168, right? Okay. And then, now that we know delta P, right, we can see what the two momentums were before and after, right? And now I can find what the average force was. This is part B now, right? We know in part B, the average force is multiplied by the time, or is equal to the change of momentum divided by delta T. We know what the delta T is, so we take our number, 1. Oh, and I should have denoted this was up, right? So this is 1.168, and we're going to divide by the time of 0.01. We should see the average force exerted by the floor on the ball will be 116.8 newtons up. Okay, so that's a little insight into, hopefully that wasn't too much, right? The last question is just somewhere where we like, it's an extension question, right? Where we don't have to provide you with the exact information that you need in order to solve for the change of momentum, right? We can use some of our prior knowledge in order to do questions like this, right? And I think that's what's great about physics is it kind of pulls upon, not only is it pull upon all your math skills, right? But it kind of like, it makes you see the world as a series of connections, right? And then we study those connections through each of the units that we study, right? And we saw that today when we replaced acceleration with a kinematic equation at the very beginning of the lesson, and then we came down to the end of the lesson and we used an energy argument from this morning's lesson, right? It was cool from that standpoint. Okay, so that's it. There's some homework questions posted in Minds Online, and if you guys have any problems, let me know. Okay. Anyway, that's that. Okay, that's up there for you guys to watch.